Well, this is what, session 5, and the topic tonight is your HF transmitter. Well, the last couple of sessions were rather intense. We kind of crammed in a lot of stuff on the last 2 sessions and quite a few slides. This one, however, is 89 slides, and I think we're going to just cover this one topic tonight and let it go. I'm tired. I still want to eat, and I haven't finished my dinner, so I'm going to just cover this for this evening, this topic. Share a few pictures of some of my HF equipment and maybe even some of my VHF equipment. But here we go. We'll get started here. And I want to get to the right page in my copy of the book. Give me just a few moments. We covered some of that wonderful skywave excitement that you're going to run into with HF yesterday, and there you go. So, okay, page 97. If on that page you're looking at it, the little Elmer point, you can expect to spend about 800 bucks. Actually, you can get away with a little bit less. I have a Kenwood 940 here that I paid 600 for, and I also have a Kenwood TS520S I paid 350 for. However, it needs VFO work and a little bit other stuff that I got to get done. So at any rate, it's going to be up to you what your budget is going to be. So let's get into the topic here of the HF rig itself. There's we're talking about some modulation here. So the instantaneous power level of the signal will vary with amplitude modulation. And predominantly what that means is um, if your single sideband is a type of amplitude modulation, and when you're using single sideband, there is no carrier, but the amount of modulation you put into the signal will vary the level as the signal as you talk up and down. We'll get into some pictorials here. I think I might even have some. Let me look here real quick. I think I have a technical folder that might show some of that. Okay, maybe I don't. Not readily handy. Maybe it's in here. Okay. At any rate, I think there's some stuff here in the book too that kind of shows a little bit about that. But anyhow, let's move right along. So amplitude modulation, single sideband is a form of that, not strict AM. And if you recall, AM, straight AM includes an upper sideband, a lower sideband, and a carrier signal. Okay, in a single sideband transceiver, the balanced modulator processes a signal from the carrier oscillator and the speech amplifier and sends it on to the filter. So if you look in the diagram there on page 97 and up here on this view screen, you have an input modulating signal there that goes into the balanced modulator. You also have an input carrier signal. Okay, but the F1 filter will pass either the upper sideband or lower sideband, and the carrier is actually removed from the signal, and then that goes out to the other circuitry for broadcast in the open airwaves. Again, the balanced modulator produces an upper and lower sideband signal with the carrier reduced to near zero. The upper and lower sideband signals are then fed into a narrow filter network, which cancels out either the upper or lower sideband signal based on other settings of the radio. Now, most modern radios, like I say, will automatically, when you switch bands, will automatically switch to the proper sideband. My Kenwood 940 does not. So if I'm using the upper HF bands like 20 and 15 and 12 and 10 meters, which are all upper sideband, and then switch over to the lower side frequencies of the HF bands like 160, 80, and 40, um, I have to manually select lower sideband. Otherwise, if I don't do that, I'm going to hear weird stuff. It's not going to sound right. So I have to select either upper sideband or lower sideband. Same thing with my older Kenwood TS520S. I've got to select either lower sideband or upper sideband. Now, on my ICOM 706, which is a little portable radio, as a matter of fact, I'm going to go ahead and let's see. I want to bring up some of these radios right now. Well, there's I use this, that's my Hallicrafters. I use that for CW as a novice. And let me see. Oh, one of my first CBs. See if I can get down here. Okay, this is the ICOM 706 MK2G. And it has a lot of little bells and whistles on it. It will automatically select the sideband I wish to operate on, and you'll see that since this is on 20 meters, it's automatically on USB. We'll cover that one a little later. There we go. On the 520S, you'll see that you have to select either CW, upper sideband, or lower sideband, and here's the band select switch over here, and some other stuff that you can do with this. This is a hybrid rig that has tube finals in it, but everything else is pretty much solid state. You actually have to switch this little switch into the send mode for full break-in CW, and also if you want to transmit. So if you're on voice, this still has to be, well, this is a heater switch. This is the send button over here. The heater switch actually heats up the tubes. My apologies for that. But the send switch is important for CW operation. Let's see if I can find. Okay, here's the Kenwood 940S, and again, here's the lower sideband, upper sideband, CW, AM, FM. It's pretty neat. It does FM as well, and a bunch of other controls, but you have to manually select the sideband. Okay, the phone emission that uses the least bandwidth as far as voice is concerned, we're talking about voice communications here. The least bandwidth, the single sideband, and if you recall from previous lessons, and especially in the tech, it's usually about 2.8 kilohertz bandwidth for the modulated signal. And as it says here, the modern high-frequency ham radio may include adjustable transmit single sideband filter networks that can decrease the amount of occupied bandwidth on transmit from the normal 2.8 down to 2.6. A lot of you can even get down to 1.8, which and still have some fairly good readability. Those filters, you can put extra filters in your rig to narrow the pass band on receive, particularly when the bands are crowded. But as it says here, when you get down to these lower bandwidths, you kind of lose some of the bass response. But that's okay. It's not really all that important. So you want the intelligibility, and the higher frequencies and the voice range have the intelligibility. That's why you hear so many women as dispatchers on for police and fire because they have a higher pitch voice. It's better for clarity and being able to provide the intelligibility to get the proper message out. So this is a typical block diagram of your HF transmitter. You have your mic, you have a microphone amplifier, balanced modulator, and there you have the crystals referenced for the lower sideband and upper sideband um, portions of your transmission, carrier oscillator. Then it goes into a crystal filter, IF amp, IF mixer. Then you have a second oscillator, which provides additional mixing, IF amp, VFO mixer, and then you have your power output and out to the antenna. So that's pretty much a simplified diagram. Most HF radios sold out there on the market these days are barefoot at 100 watts of power nominal. And that's typically the 100 watts is typically in the side for the sideband portion. If your radio has AM, and most of them do, the actual power output on the carrier is going to be reduced, maybe anywhere from 40 to 60 watts. But AM, FM, and other modes of transmission, a signal on the carrier signal. The carrier does use some of the power, and that's why you're not going to have a full 100 watts out there. It's not a big deal, though. Not many people use AM, but there is some AM activity out there, particularly when you're on 75 and 160 meters. And you might find an occasional AM QSO going on for 40 meters. At any rate, carrier suppression in single sideband allows the circuitry of the radio to put additional power into each sideband signal. So your signal travels farther with this additional power for that exciting DX skywave activity that was mentioned in yesterday or the last session. There are speech processors on most radios. There is a caution to them because if they're misused and not used properly, there can be a distortion on your signal and you lose some intelligibility out there, and you may sound really garbled. Am I up on the mic now? And you don't want to really sound garbled, but just a little bit of speech processing can be beneficial in increasing some intelligibility of your transmitted voice signal and your average power. And if conditions are really bad, again, you might want to use that speech processor. And if it's really crowded, the speech processor can help cut through some of the noise and the din of other QSOs going on. But still, it needs to be used with caution. And when you have good conditions, your noise levels are low, you don't have crowded bands, it's always best to leave the speech processor off. Turning on your transceiver speech processor will not increase PEP output power if you are 100% modulated. It will increase the average power, which many times makes your signal sound too hot for comfort. So again, stay off that speech processor button unless it's absolutely necessary. So you have that new HF transceiver, and you're going to reward yourself with when you pass your exam, and it has a built-in transmit safeguard called ALC, or automatic level control. You're going to get specific instructions that you really want to make sure that when you tune your radio and you get ready to get out there and get on the air and everything, that you don't want to overdrive the ALC. So there are specific instructions on how to properly adjust your transmitter so that your ALC does not does not cause problems, because the ALC acts as an electronic governor to throttle back transmit power in case you overdrive the input circuits with too much mic gain. Or there's a possibility that you might provide too much drive from your computer if you're doing data. There is a multimeter on the rig. Let's see. Let me kind of bring this up here. The meter is typically, I'm sorry for the picture, it's not very clear, but I have to zoom in here. But the multimeter has various functions here. It can even, if it has the capability, it can even tell you if your SWR is okay. But this little switch down here will tell you how much grid current you're putting in, the ALC, the power, the SWR, all that information. So it's a good idea to kind of keep an eye on that to make sure that you're transmitting properly. It'll go a long way in helping you make sure you're not driving it too far, too hot. See, it says look for a small now and then jiggle of the ALC indicator, which will indicate proper drive levels. If you overdrive the ALC section of your transmitter, you'll see the ALC meter going up into the red danger area. So if this happens, you immediately back off the mic gain or the computer drive power to your transmitter. And it may also do that if your speech processor is too hot as well. Hi, Cohen. Glad you're here. Okay. So, we're talking little bit about some digital modes here. Sound card digital modes work by applying AFSK signals to the input of a properly aligned single sideband transmitter, which then become FSK signals. So we talked a little bit about this in the digital topic a few sessions back. So an FSK signal should consist of two and only two frequencies. Intermodulation distortion, usually resulting from overdriving a single sideband transmitter, will create additional frequencies near the desired ones, and these additional products can make the signal difficult or even impossible to decode, and may also cause interference to other stations, which is called intermod, if it is severe enough. So when using sound card modes, the ALC should be disabled or the audio level reduced to the point where no ALC action occurs. And the proper drive level for a sound card mode is when the PEP output power of the transmitter is between 25 and 50% of its maximum capable peak envelope power. So there is a drive control. Let me see if I can. There's a drive control right here. This is a combination. There's the mic gain as well as a power control right behind this little button here, and so you can kind of throttle that back and that controls the driver going into the final amplifier. The ALC output jack on your new transceiver needs to be tied into the ALC input jack on that linear amplifier. So if you're going to be running a linear amplifier, there's certain ways that has to be hooked up. All right, what page am I on here? There we go. So the question is asking here for G4A05 is, what is a reason to use ALC with an RF power amplifier? Okay. It gives your equipment the handshake when the drive level is correctly set. So without this simple plug-in connection between the amplifier and radio, the amp could be overdriven and the signal distorted due to excess drive. So the amplifier could go into thermal meltdown from being overdriven. Be sure to hook up the needed ALC handshake cable between your rig and your amp. I do have I have a Ameritron AL811. It's a 600 watt amplifier. Not sure if I don't have a picture of it, but I can bring it up real quick. Let's see here. Oh, that's a okay. My cough is coming back tonight. Isn't that nice? I love it. Stupid cough. All right, I'm back. So this is the amplifier I have. You'll notice there's no 10 meter selection on here. However, with a slight modification on this aux circuit, you can get 10 meters on it. But in order for this to operate properly with your radio, you have to have the proper set of cables that run between the amplifier and the radio. And making sure that you have that also that ALC handshake. Okay, don't run excessive drive power when operating in digital modes. Again, we're just kind of rehashing the same information. Turn that drive back so that you're somewhere between a quarter and maybe 50% of the power. Try going with a quarter of the power first. So sending ultra long messages with excessive power can cause the radio to get red hot and ultimately damage a power amplifier output device. So make sure you have your HF radio ventilated properly. It does have a built-in fan. You may need to add another fan if you're going to be doing long transmissions, but make sure you don't obstruct the airflow. Get back over here. So if you overmodulate it on HF, you're going to spread your signal over a wider bandwidth than that of a properly modulated HF signal. And if someone says you're splattering, turn down that mic gain, turn off the speech processor, because that's what's causing it. And if you were to look at a spectrum analyzer while you're transmitting, if you're overmodulating, you might see signals kind of just adjacent to where your regular modulated signal is, and even could be across the band. You could be creating spurious emissions all across the band if you're too hot. All right. Most of the newer HF transceivers have a speech processor button that will turn the processor on and off. Turn the speech processor off because it can also bring in excessive background noise, and it may cause your signal to sound distorted. It can also cause the signal to splatter to adjacent frequencies. So leave it turned off as a rule. But learning how to use it and use it properly can help you actually achieve the QSO you'd like to get in a pile-up situation possibly or other circumstance. So if you turn the microphone gain too high on single sideband, the signal will sound distorted. The signal waveform shown on an oscilloscope has the top clipped off, so it has a flat top. So he's got his little oscilloscope here, and he's got it hooked up somehow, and um, it's clipping due to the limiter circuit. So you're not going to sound very intelligible, and you won't sound very intelligent either. Okay, so in reference to the type of transmitter performance, a faithful reproduction of your voice over sideband depends on equipment that has excellent linearity. And with the new digital signal processing techniques, or DSP is what it's abbreviated as, when modulating, plus a new family of aftermarket high-performance microphones, the two-tone test that enables you to the two-tone test that enables you to view the waveforms on an oscilloscope is a great way to test for transmitter linearity. Even though the two-tone test is your best answer for transmitter linearity, I always like to ask fellow hams simply how I sound to them coming over the radio, so no oscilloscope needed. Generally speaking, when you do make a contact, it's common courtesy anyway to as a ham to say, you know, your signal isn't quite 5.9. There is some chirping on it, or you know, some other. I do apologize. This is weird. Anyway, you can always ask if they don't tell you how you sound. You can always ask how you sound over the air. Sometimes when we get on the 10-meter net on Tuesdays and Thursday evenings, we'll let each other know how we sound, whether our signal is light or our modulation's bad or something of that sort, or a hum, something of that sort. So it is a courtesy. It should not be an offense. No ham should take offense if you're on the air and somebody says, "Hey, there's a hum on your signal." Well, that gives you the ability, you know, something you got to look for something that might be causing that hum, and because you want to be at peak performance, make sure that you're not transmitting stuff out there on the airwaves that should not be out there other than your melodious voice. So if you plan to regularly service your own equipment, you can find a little warbler box that generates two non-harmonically related audio tones for testing. So the device may either be plugged into the transmitter mic input or the mic held up to the speaker on the device. But the two tones must not be harmonically related in any way in order to provide the best test. So on the, I don't know if on the CD that comes with this course, this is not the CD course, but what comes with this, I wonder if it has it on there. I've never listened to the CD personally. Maybe I should. Okay. Getting a little medicine down my throat to stop coughing. So this is talking about the modulation envelope of an AM signal. And while sideband is the predominant phone mode on HF bands, and it's like I said before, there is still a significant amount of activity on full carrier, double sideband, or amplitude modulation. Information is impressed on an AM carrier by alternating the amplitude of the RF wave in accordance with the applied audio signal. The envelope of the AM signal is the outline or extreme outer limit of the radio frequency signal. If you have your book open, there from the previous question on page 102, it shows kind of how an AM signal would look like there. So 100% modulation is defined as when the envelope goes to zero, pinches off during negative modulation peaks, or increases to twice the amplitude of the unmodulated RF carrier. I hope you can't hear me when I cough, when I mute. Anyway, the envelope of the AM signal is the outline or extreme outer limit of the radio frequency signal. One thing about the human voice, it is asymmetrical, so the positive and negative modulation peaks can be very, very different. Okay, why won't you change? Come on. There we go. All right, an oscilloscope is your best piece of test equipment if you're rather technical at being an amateur operator. And a lot of times, for over the decades, of course, when I got involved in it, you had to be more technical. Today, there's a term used, armchair operators. They go out, buy a piece of equipment, hook it up, and throw an antenna on the line, and as far as they're concerned, they're good to go. But it's good to have some technical skills so that you can uh, define and troubleshoot and make sure that you can keep your equipment and your antennas and other peripheral devices in top operating condition. So it's good to have some technical skills. I do have an O-scope. Um, I know how to use it. I've used one for years. But the O-scope has a horizontal and vertical channel amplifiers. And if you look on page 103, kind of gives you a shows a picture there of a oscilloscope and kind of points out some of the different controls on an O-scope. And here we are. We even have a picture of it here. Woohoo! Yay us. So it is your best instrument to check for transmit signal quality. When magazine editors review the waveform of a CW signal or a two-tone test, they usually show photographs of the oscilloscope display. And as you see here, this O-scope is actually showing an AC waveform. Okay. Let's see, next. Getting ready for my next cough. We take the attenuated RF output of the transmitter and couple it to the vertical input of an oscilloscope to check the quality of the transmitted signal. You got to be careful when you do this that you're not putting too much RF power into the O-scope, that the O-scope has the proper attenuated probe. And the best way to do it, though, is to make sure that you're not driving it too much. That way you can get a good signal source. see a pretty little wave form and all that other good stuff. So when you whistle into the microphone and look at the resulting waveforms on an oscilloscope, you'll see that only an oscilloscope can truly represent complex voice waveforms. And that way you'll be able to precisely measure how your voice is doing. All right. So older tube type HF equipment, like I showed you there earlier, like the old Hallicrafter stuff and the hybrid Kenwood 520S, they incorporate a transmit and receive relay to toggle the output and input of antenna connections. But your newer HF transceivers have a solid state switching between receiving and transmitting. So in order to accommodate an external linear amplifier, you may need to review the time delay transmitter keying circuit to allow the amplifier to switch on just before it begins to receive transmit power from the transceiver. And when your newer rigs, of course, there's all kinds of different connections on the back of them. Let me see here if I can pull it up. Where am I? Do. Okay, let's see. This looks like the best one right here. Cancel that. Get back over here and let me bring this up. All right. Look on the back of the 940S here. We'll zoom in a little bit. You have several connections, not the least of which is, being important, of course, is the antenna connection, a ground connection, and you also have, you can put in another receive antenna. Some people will put up a nice beverage antenna because they do receive very well. I don't, and you can actually control whether it's on or off. You can put a transverter with this. If you wanted to run 6 meters, you can get a 6-meter transverter and plug in there. And then you have this little remote connection. And this remote connection on this particular rig, one of the cables that I have that goes to my Ameritron amplifier plugs into this particular jack right here. These over here, we have some accessory connections for different things. I don't know exactly what they're for. There's actually in the manual, they have pinout information that if you wanted to be a little creative and control something, you could, or have some accessory plug-in, you could do that. Probably this would work, have some kind of connection to a computer for operating digital. Interestingly enough, if you have a teletype machine, this rig right here will connect directly to a teletype machine. There's your RTTY plug, an external speaker, and then your phone, your CW key can plug in there. Now that CW key, it can either be paddles or it can be a straight key, and because it does have a built-in keyer in there. This particular rig as an option, and it looks like it has it on there as an option, also has a built-in, you can get a built-in antenna tuner with it. So there you go. Okay. This talks a little bit about, I presume, some tube type equipment. If you have tube finals like the TS520S that I have, if it has tube finals, they really need to be neutralized. So, um, and even in your amplifier, if I were to change the tubes in the 811, it has 3 final tubes in it to give me 600 watts. I would have to neutralize all of them, and it's usually best that if you order tubes, not to replace just one. The best thing to do is that if you have a tube that you suspect as being kind of weak or soft, or maybe both tubes as being weak or soft, order a whole set uh, and make sure they're a matched set. And what I mean by that is that the manufacturer, when they put them together, they will match tubes to make sure that they're all going to perform in a similar manner, and they will be easy to neutralize once you install them. So you need to neutralize those tubes, and it'll eliminate the possibility of self oscillation. All right, I knew it was in here. We have some diagrams of modulated RF signals. So, however, now we're going to talk about FM, obviously. Okay, a type of modulation that changes the frequency of an RF wave is called frequency modulation. And in frequency modulation, you'll see down here, especially on the bottom right here, the signal that you put in, this being the voice signal just above it, the signal you put in will vary the frequency of the modulated signal. In an amplitude modulated signal, however, the voice that's introduced into it will vary the amplitude of the carrier or the modulated signal. So that is the difference between AM and FM signals. FM is frequency modulated, it slightly changes the frequency of the signal, typically in FM by as much as 5 kilohertz. So 2.5 kilohertz on the low side, 2.5 kilohertz on the high side. But it's about a 5 kilohertz signal um, that is modulated in an FM carrier. Why they're talking about VHF in this section is beyond me. So inside the VHF FM transmitter is a low power oscillator that operates at high frequency levels. It's the job of the multiplier. Stand by. Okay. It's the job of the multiplier to select a harmonic of this signal to produce the desired operating frequency. So remember, the harmonics are like chords on a piano. Each note is 1/3 or so higher than the last, and they're mathematically related. So it is logical that the stage of the transmitter is called a multiplier. So it's the answer choice that is mathematical for G8B04. Okay. Okay, for this particular question, it's talking about the bandwidth, the total bandwidth of an FM phone transmission having a deviation level. So you can calculate the answer of this question by multiplying 2 times the sum of the deviation and the modulating frequency. So the deviation is 5 kilohertz plus 3 kilohertz of audio modulating frequency, which gives a sum of 8 kilohertz. 2 times 8 kilohertz equals 16 kilohertz. This would be the total bandwidth of the FM phone transmission. They're much more narrow these days, I think. You'll notice that as far as repeater frequencies are concerned, there is about a 15 kilohertz separation between the designated frequencies of the repeaters. So if you take like the 146.82 repeater, the next frequency of that would be 146.835, 825, no, 835, I think. Let's see. Yeah, that'd be right. So you really don't want a bandwidth that wide, but for the purposes of this question, again, if you have 3 kilohertz of audio and 5 kilohertz deviation on your radio, your total bandwidth of the FM phone transmission is going to be 16 kilohertz. The deviation of any frequency modulated transmitter is increased when you follow the oscillator with a frequency multiplier. So in fact, the deviation is multiplied by exactly the same factor as the radio frequency. If we multiply the oscillator frequency by 12 to get the final output frequency, the deviation is multiplied by the same amount. So this means that if the final deviation is 5 kilohertz, we can divide that by 12 to come up with the required oscillator deviation. 5 kilohertz divided by 12 is 4.16, or in this case, we're rounded to 416.7 hertz. That's where your frequency multiplier rests. A reactance modulator produces FM when applied to an oscillator. The phase modulation when applied to and phase modulation when applied to a subsequent amplifier stage. This is a very simple circuit. I had a radio. As a matter of fact, I had this radio, a Lafayette HB740, and of course, this is a CB radio, and it was converted to 10 meters. It was converted to 10 meters FM for repeater operation. And it was a simple circuit to do exactly what was described in this question here. We put a reactance modulator in to feed the audio onto the signal, creating a frequency modulated, in this case, it was actually a phase modulated signal. And it worked quite well. So some of these controls were changed a little bit to accommodate the split repeater operation too. A type of modulation that changes the phase of an RF wave is called phase modulation, or PM. And still, again, very similar to frequency modulation. It's just changing the phase a little bit. The efficiency of an RF power amplifier is calculated by dividing the radio frequency output power by the DC input power to that stage. In other words, if you get 100 watts of CW output power with 250 watts of DC input power, your efficiency is 40%, which is about typical. This is all within your bare bones radio. Since the RF output stage is by far the primary consumer of power in any modern HF rig, you can closely estimate the RF final input power by looking at the total DC current drawn by the rig and multiplying that by the DC voltage, which is typically around 13.8 volts. Got to be very careful here, because unless you have a rather uncommon PEP meter, You cannot determine RF power output using speech or whistling or any such method. You must use a CW carrier, and single sideband transceivers do have a tune function specifically for this. And I can show that to you on, let's see, where is it? A lot clearer on, there it is. On this rig right here. This is a TS520S. It has a tune position here, okay, to help make sure that you're getting the right output power, and that everything is operating properly. So the peak power of the human voice can be over 6 times the average power, and a typical peak RF output power, as well as the DC input power, can be many times that what your slow moving meters can indicate. But that tune position helps to accommodate your ability to kind of figure that out. For the most part, just divide the radio frequency output power by the DC input power to that stage. Your answer to that would be, where are we? 7B8. Yeah, your answer to that would be B. Answer B. Is that right? Yeah. Okay. Okay, this particular question has you looking at an oscilloscope that indicates 200 volts PEP across a 50 ohm dummy load. 50 ohm dummy loads are very important. You might want to make sure you have one of those in your shack. So we're looking for power. We have resistance in ohms and voltage in volts. And again, consulting that magic circle on page 132, there is one here in the book, I guess, somewhere. We find the relationship for power when we have resistance and voltage to be voltage squared divided by resistance. In this case, we have 200 volts peak to peak. We need peak voltage for the calculations. 200 volts peak to peak divided by 2 equals 100 volts peak. Peak to peak is including the positive above the zero plane and the negative below the zero plane. So you divide that in 2 and you get one side, or just 100 volts peak on one side. But the question is asking for peak envelope power, which is calculated at the root mean square, RMS, of the output power according to the FCC. And we continue this on the next slide. Your RMS is 0.707. Remember that 0.707 times voltage peak. So voltage RMS is equal to 0.707 times 100, or 70.7. So now we can find the power using the formula. Power is equal to 70.72 divided by 50, or 50 ohms, which is equal to 49. Let's see. Now, what did they do here? Okay. They didn't quite do the formula properly. Look down at the bottom there. You see how they do that. 200 divided by 2 equals 100 times 0.707 equals 70.7 times 70.7 equals 4998.49 divided by 50, which is your 50 ohms, which is equal to 99.96 rounded to about 100 watts. And up there in the red, they kind of didn't do that properly up there. That first 50 shouldn't even be there. So go by what's down here at the bottom. Don't look at this up here. Okay, in this question, they're talking about what the output PEP is. Again, take half of the peak-to-peak voltage to obtain peak voltage and multiply 250 by 0.707 and square the result by multiplying it by itself and divide by 50. So here's your calculator keystrokes. 250 times 0.707 equals 176.75 times 176.75 equals 31,240.56 divided by 50 ohms is equal to 624.81, which rounds off to about 625 watts. You're right, Cohen. It is right in the book. No, it isn't. No, it's got the same kind of stupid formula in there, Cohen. If you look about, let's go back on this one. 06. Again, it has that same. Oh, what they did was they squared it in here. I see what they did. Okay. They squared 70.7. They show it in there. Okay, I see what they did in there. Right. You're right. Okay. I was wrong there. Okay, very good. Thank you for pointing that out. An unmodulated carrier is simultaneously peak and average. So the ratio of a peak envelope power to average power on a steady unmodulated carrier is just simply 1. Very simple. Just remember it's 1. Remember, a steady carrier illustrates both peak power as well as average power. So if your watt meter reads 1060 watts average, this is the same power as peak envelope power. Nice. Okay, the decibel is used to describe a change in power levels. It is a measure of the ratio of power output to power input. A 2 times increase results in a change of 3 dB. So that's rough. That's kind of a rough estimate. So if you have a 10-watt transmitter and you multiply it by 2 to a 20 watt amplifier or power output, that's about 3 dB increase in level for your power output. So when you look at antenna specs, you might see something that says, okay, this antenna has a gain of 6 dB on 2 meters. So really what's happening is that you get 4 times the increase. If you put 10 watts, let's say you put 10 watts into the feed point of that antenna, uh, we'll just go ahead and count any transmission line loss as negligible in this case. Putting 10 watts into the base of that antenna with a 6 dB increase um, is going to be about the same as a 40-watt output on the antenna. Okay, seeing an S meter change from S8 to S9 is an increase of a single S unit. One S unit is 6 dB, and 6 dB is a 4 times change. So here's how it works. The dB of power. So if it's 6 dB, you get 4 times the change. You get 2 times the change. Like I say, 4 times if the antenna says 6 dB, it's 4 times the change. 10 watts in, 4 times 10 watts is 40 watts. An S meter reading of 20 dB over S9 compared to just an S9 signal illustrates the signal is 100 times stronger. Yeehaw. Yeah, you get somebody coming in, you're looking at your meter, you have an S9 uh, level, but then it goes above that as far as a dB reading is concerned. And that's what happens. You get a 100 times stronger signal at 20 dB over S9. So a Class C amplifier is ideal for high efficiency, nonlinear amplification of Morse code and frequency or phase shifted digital emissions. Varying amplitude emissions like single sideband or AM would not sound right if the amplifier is operating in the Class C region. But for CW, it will work great. Okay. So remember that Class C, CW, even for digital modes, um, it's ideal for that. Oh boy. Now it's up to you whether you learn code or not. But CW will always continue to be a popular mode for ham operators, even though the code test has been completely eliminated. A little bit of CW only transceiver, a small CW only transceiver operating Class C offers high efficiency with little current being consumed from the battery in between dots and dashes. So a Class C amplifier equals high efficiency. Now, a Class A amplifier in an HF transceiver is usually found within the microphone input stage where low distortion is an absolute requirement. So when you're using voice, Class A amplifier is the must have because otherwise, with a Class C, it'll sound distorted. Class A, it won't. Here we have a picture of a linear amplifier. Linear amplifiers will indeed pump up your output waveform exactly as it appears to the amplifier input, if it's a linear amplifier. Anyway, it's unwise to run any linear amplifier on HF mobile or on a simple home antenna until you're experienced with your equipment and discover that 100 watts can work all around the world. Yep, it sure can. You'll find that 100 watts in a wire will get you around the world without an amplifier. On the load control, on that old power amp, seasoned hams will tell you to tune for maximum smoke. Well, not really, but tune for a maximum power output reading, making sure you do not exceed 1500 watts output, which is no danger with my AL811, which maxes at 600. All righty. Okay, last slide before the questions. Isn't this great? If you look on page 109 at the bottom there, you have a little Elmer point that says, don't run out and just buy a linear amplifier. Okay. All right, this last question here. What reading on the plate current meter of a vacuum tube RF power amplifier indicates the correct adjustment of the plate tuning control? A vacuum tube amplifier is operating properly when the tuning is adjusted for a dip or minimum current, and the loading is such that the plate current at the tuning dip is at its rated value. That's what all those controls are for on there that I was kind of showing you before. Let's go to, well, I can do it with this. The drive controls the input to drive the final tubes. There is a I think it's a 12BY7 or something like that, driver tube at the input of the two output tubes, 6146Bs in this rig. So the drive gives you once the main tubes are and the circuitry is tuned properly, the drive control will drive maximum power out of this rig, and you can get about 100 to 120 watts out of this thing. But you want to make sure that the plate is within the range of the selected band, and then you want to adjust the load on this. So by doing that, you can make sure that your ALC isn't overdriven. You can make sure that your plate current is set properly, and uh, the plate loading is set properly with these three controls. And that will give you the maximum or the desired output that you want. So looking down below here, um, oh, yeah, you should monitor the RF output if possible. And probably you're going to have a meter attached between the rig and the antenna anyway, and it's going to have an RF output while you're also watching the meter on your rig to make sure that you've adjusted the current and the loading properly. So the loading should never be increased beyond the point where output power no longer increases. So if your output power doesn't move, if you got to maximum, don't you there's no need to adjust the loading any more than what you've done. So whenever any adjustment is made to the loading, the tuning should once again be checked for a dip to make sure that your plate current is at a minimum, and that should always be the last adjustment made. It also needs to be adjusted if you change frequency by more than a few kilohertz. That was one of the things about your tube rigs is that once you tune that circuit, if you moved a little bit off frequency, a few kilohertz, it was always a good idea to make sure that you retuned the output amplifier. All right. Any questions before we get into the questions? And once we do this, we'll kind of wrap it up for the night. If you're ready to go, we're going to continue on with the HF transmitter question pool. So, what type of modulation varies the instantaneous power level of the RF signal? Okay, we're talking about a single sideband signal here, and it's going to change the power. In other words, up and down, and that actually relates to amplitude. So your proper answer here is D, amplitude modulation. All right, which circuit is used to combine signals from the carrier oscillator and speech amplifier, then send the result to the filter and some single sideband phone transmitter? And we were talking about how we make sure that these all these components and elements of your voice are properly balanced. So it goes through a balanced modulator. D is your answer. Okay, which of the following is used to process signals from the balanced modulator, then send them to the mixer in some single sideband phone transmitter? Remember, it has to, once you balance that signal, there has to be a filtering process so that only the desired sideband is actually going out. So B is your correct answer. It goes into the filter circuit. So which of the following phone emissions uses the narrowest bandwidth? No brainer here. Single sideband, 2.8 kilohertz to 3 kilohertz, somewhere in that neighborhood. So it is, and you can actually narrow it down a little bit more without too much distortion. So, what is one advantage of carrier suppression in a single sideband phone transmission versus full carrier amplitude modulation? It has nothing to do with audio fidelity. There is not a greater modulation percentage, and it has nothing to do with simpler receiving equipment. It actually, what it does is see the available transmitter power can be used more effectively. So, all the power that would go into an upper and lower sideband as well as a carrier is then transferred over to the single sideband. That's why when you see advertised on the CB boxes, "Ooh, look at this. You got 120 channels and you have up to 12 watts of power." Well, what they're doing is you still have a 4-watt transmitter on AM, and all you're doing when you do sideband is you're transferring all that power that is normally contained, you know, uh, on all 3 elements over to one sideband, and you get an effective power of 12 watts. And believe it or not, you can even talk around the world on 12 watts. So, what is the purpose of a speech processor as used in a modern transceiver? Okay. When you look at these other answers, it has nothing to do with bass response. It does not prevent distortion of voice signals, and it does not decrease high frequency voice output to prevent out of band operation. That's not what the purpose of the speech processor is. Rather, it is increase the intelligibility of transmitted phone signals during poor conditions. Again, this is something you might not want to use unless absolutely necessary. Hmm. So, which of the following describes how a speech processor affects a transmitted single sideband phone signal? Okay. It will not increase the peak power. It does not reduce harmonic distortion. It does not reduce intermodulation distortion. However, it does increase the average power. So think of that speech processor as being rather average. So, what control is typically adjusted for proper ALC setting on an amateur single sideband transceiver? Be very careful when you look at this. There is no RF clipping level adjustment. It has nothing to do with antenna inductance or capacitance. Attenuator level, no, there's no such thing. It's really the transmit audio or microphone gain that is adjusted for the proper ALC setting on your transceiver. So, what is likely to happen if a transceiver's ALC system is not set properly when transmitting AFSK signals when the radio with the radio using single sideband mode? Okay, what is likely to happen if the ALC is not set properly? Uh, the ALC will do nothing to invert the modulation of an AFSK mode. Um, when using digital modes, too much ALC activity can cause transmitter to overheat. No, it will not. And based on the fact that A is incorrect and now C is incorrect, D is definitely incorrect. So the improper action of an ALC will distort the signal and will cause spurious emissions if you have too much uh, microphone gain or phone gain on turned on there. So you got to be careful about that. Do, 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 do. Come on, what did I just do? There we go. So, what is a reason to use ALC with an RF power amplifier? This one is pretty easy to spot right here. It doesn't balance, it doesn't reduce harmonics, it does not increase the overall efficiency, but it does reduce distortion due to excessive drive. So the proper adjustment of the ALC is necessary so that you don't get distortion with an excessive drive. What condition can lead to permanent damage to a solid-state RF power amplifier? What condition can lead to permanent damage? If you have excessive drive power, D is your proper answer here. If you have too much drive into the RF power amplifier, you could damage it. So which of the following is an effective overmodulation? Okay. Well, overmodulation has nothing to do with the first three, but it has everything to do with D, excessive bandwidth. You can splatter across the band and interfere with somebody else's QSO going on. Which of the following can be the result of an incorrectly adjusted speech processor? Well, if it's incorrectly adjusted, you can get distorted speech, you can get splatter, you can also get excessive background pickup if you have a noisy environment. So, D, all of these answers or all these choices are correct. What is meant by the term flat topping when referring to a single sideband phone transmission? Remember the little picture there that if you have a flat top, it will actual cause signal distortion. Again, watch out for this one because A includes that word signal distortion, but it also includes insufficient collector current, which is no, not the correct answer. And if the ALC is properly adjusted, you're not going to get flat topping. And it has nothing to do with the transmitter carrier being properly suppressed. But C, signal distortion is caused by excessive drive, causing flat topping of your audio signal. What type of transmitter performance does a two-tone test analyze? Man, this is so simple. It just tests the linearity of your transmitter. How linear is it? And really, you do not want them to be harmonically related, which is probably going to be the next one of the next questions. So, what signals are used to conduct a two-tone test? And I just gave away the answer: two non-harmonically related audio signals. What is the modulation envelope of an AM signal? Okay. The it doesn't have anything to do with the carrier frequency that contains this, although there is a carrier there for AM. Um, and spurious signals are not even part of the equation or the bandwidth of the modulated signal. However, the modulation envelope is the waveform created by connecting the peak values of the modulated signal, or peak to peak. The high side on the upper part and the lower side, that's your peak values of the waveform or the envelope of the AM modulated signal. What item of test equipment contains horizontal and vertical channel amplifiers? This should be a no-brainer. It's the oscilloscope. Which of the following is the best instrument to use when checking the keying waveform of a CW transmitter? Well, we've kind of beat this little horse. It's an oscilloscope, of course. So what signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? Okay. Um, the vertical input of an oscilloscope, you need to put an attenuated RF output of the transmitter. This is what I was saying earlier. You don't want to drive too much into that O-scope. You could actually mess up the front end of the O-scope if you put too much power into it. And there are special probes for oscilloscopes to make sure that if you're doing RF, it'll attenuate properly, and it's best also to reduce the power as much as possible on there. But with that, you can check the RF envelope pattern of a transmitted signal on the oscilloscope. So which of the following is an advantage of an oscilloscope versus a digital voltmeter? Well, a digital voltmeter really has some limitations, okay? Um, it can do a variety of things, uh, one of which is voltmeters, but I'm presuming they're also meaning multimeter here. But specifically, the voltmeter will measure your voltage. However, an oscilloscope will measure or give you an indication of complex waveforms that can be measured. So, why is a time delay sometimes included in a transmitter keying circuit? Remember, we were talking about that time delay and why it was necessary. The transmitter keying circuit has to do with how it operates an external amplifier, but the time delay gives time for the transmit and receive changeover operations to complete properly before RF output is allowed. And what is the reason for neutralizing the final amplifier stage of a transmitter? We were talking a little bit about this, um, making sure that you have a matched set of tubes, that when you replace them, they have to be neutralized. And the main reason it needs to be neutralized is so it will eliminate your self oscillations. What is the name of the process that changes the instantaneous frequency of an RF wave to convey information? All right, we know that AM changes the amplitude. In this case, we're talking about changing changes in the frequency, and it has to do with frequency modulation. What is the name of the stage in a VHF FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency? So, the name of the stage in the transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency. This is really a no brainer because you're taking a lower frequency and you're multiplying it. So the stage is the multiplier stage. D is your answer. So, what is the total bandwidth of an FM phone transmission having a 5 kilohertz deviation and a 3 kilohertz modulating frequency? And a little bit more complex than I like to describe it. You have 5 kilohertz on either side. You get 3 kilohertz of modulation. So you add those together and then you double it and you come up with 16 kilohertz. It's almost like they're using Common Core in this. Did I say that? Oh, well. So, what is the frequency deviation for a 12.21 megahertz reactance modulated oscillator and a 5 kilohertz deviation? 146.52 megahertz FM phone transmitter. Okay, the frequency deviation. Well, when you do that calculation, and of course, if you just memorize, you can just memorize this because again, you're going to come up with 416.7. Anybody remember the formula? What emission is produced by a reactance modulator connected to a transmitter RF amplifier stage? So, what emission is produced by the reactance modulator connected to a transmitter RF amplifier stage? Remember, I showed you my little radio there, and we actually made phase modulation, which is, is compatible with FMs, especially on 10 meters. So, what is the name of the process that changes the phase angle of an RF wave to convey information? Again, we're still talking about that phase modulation, B. How is the efficiency of an RF power amplifier determined? The efficiency. Okay. Simply put, you divide the RF output power by the DC input power. Okay. So remember that RF output, that RF power and DC power are totally different. So if you have a DC input power of 250 watts, you divide the RF output power by the DC input power, and that gives you the efficiency of the RF amplifier. So what is the output PEP from a transmitter if an oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load connected to the transmitter? Okay, first off, 200 volts peak to peak. Um, your 200 volts peak to peak, you're going to basically divide it by 2, and you're still going to come up with 100 watts. What is the output PEP from a transmitter if an oscilloscope measures 500 volts peak to peak across a 50 ohm resistive load connected to the transmitter output? Remember your formula. If you apply that formula properly, you're going to come up with 625 watts, or B. So the ratio of peak envelope power to average power for an unmodulated carrier is actually, it's an unmodulated carrier. Remember this. This is a ratio of peak envelope power to average power for an unmodulated carrier. B1 is the answer. Don't get confused on that. What is the output PEP of an unmodulated carrier if an average reading watt meter connected to the transmitter output indicates 1060 watts? You really want to know the answer to this? Gosh, 1060 watts. Answer's right there in the question. Yeah, exactly. I agree, Cohen. Why do they do all that goofy math? Just wait until you go for your extra class license. It gets worse. I don't know. It's kind of funny to me in many ways. Okay, what dB change represents a 2 times increase or decrease in power? Remember, you double it, you get a 3 dB increase. Rule of thumb. Just memorize that. So how much must the power output of a transmitter be raised to change the S meter reading on a distant receiver from S8 to S9? Now, the S reading is about a 6 dB change. So you're really going to go approximately 4 times. How much must the power output of a transmitter be raised to change the S meter reading on a distant receiver from S8 to S9? So instead of putting out 100 watts, you're going to put out 400 watts, but you're only going to get a single S increase on the S scale on the distant end. What's the difference in S8 and S9? You get a 5.8 RS report instead of a 5.9. As long as the guy can hear you and the noise isn't at S8, you don't need 400 watts. So how does an S meter reading of 20 dB over S9 compare to an S9 signal, assuming you have a properly calibrated S meter? Oh boy. Well, it's actually 100 times less powerful. Um, when you and they're speaking of the actual S9 signal. So a 20 dB over S9 signal is 100 times more than S9, but the S9 is 100 times less powerful. For which of the following modes is a Class C power stage appropriate for amplifying a modulated signal. And we were talking about digital and CW modes. That's your Class C or CW, Class C power amplifier is good for CW and digital modes. And which of these classes of amplifiers has the highest efficiency? Again, the CW or the Class C is the highest efficiency. Doesn't do well for phone though. So, which of the following is a characteristic of a Class A amplifier? Well, a Class A amplifier, if it's used um, for modulating or for voice, you would expect low distortion, D. Which of the following describes a linear amplifier? Okay. And you got to be careful on this one. Okay. The linearity is what is important. Why it's called a linear amplifier is that whatever you put into it is what's going to come out. So it preserves the input waveform on the output of the amplifier. That's your linearity. Yeah, Cohen, I know that. That's why I was explaining that question a little bit. Let's go back to this. Um, where is it? Yeah. But be careful because this is the way the question is going to read on the exam. So it's asking for when you have a 20 dB over S9, how it's a confusing question, and we got to make sure that we understand this properly because either way, if it's 20 dB over S9, it's 100 times more powerful. If it's just an S9 as compared to a 20 dB over S9, it's 100 times less powerful as far as an S9 signal is concerned. But the important point here is that when you look at the other three choices and you know that it's 100, the only logical answer is going to be D or 100 times. And it matters not whether it says 100 times more powerful for 20 dB over S9 or 100 times less powerful for an S9 as compared to a 20 dB over. So we got to make sure that, yeah. No, not a problem, not a problem, not a problem. I just, wanna make sure I get your question answered. I'm sure other people might see that and say, "Oh, the book says this, and the slide says that." The important thing is that number 100. So your correct answer is gonna be 100 no matter what. Alright, let's move on up here. Good deal. Low distortion for a Class A amplifier. An amplifier which preserves the output waveform is a linear amplifier. So, what is the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier? So, when you look at you're not looking for minimum SWR. That has nothing to do with it. Um, eh, it really wasn't discussed. I mean, there's that adjustment as far as tuning your plate current to minimum. B is not even acceptable. That's going to give you a little bit of a kind of throw you a curve there. So, but B is not the correct answer. And you definitely don't want the highest plate voltage while minimizing grid current. The only real answer here is that you want maximum power output because you're going to be watching your RF output on your external meter while also watching the meter as far as your tuning is concerned. So maximum power output without exceeding maximum allowable plate current, which plate current should be at a minimum. What reading on the plate current meter of a vacuum tube RF power amplifier indicates correct adjustment of the plate tuning control? And it has to be a pronounced dip or a minimum plate current. And there you have it. So, There's a lot to an HF rig, depending on what you're going to end up with. Um, Depending on your budget, what you want compared to what you can afford, and for me, it was like I was a licensed, general class. Well, actually, I had my novice class license, but I really didn't get on the air until I bought my little Hallicrafters, my 75-watt Hallicrafter set from a fellow ham who had no need for it anymore. So I bought it for 75 bucks, threw up a wire inverted V antenna in the backyard, put a tuner on it. I actually got a tuner that was homebrew. That thing was wonking. It could tune up a wet noodle, I think. And I guess my total investment was probably less than 150 bucks to get on the air for HF. And the furthest I ever talked was New Zealand, which is almost the opposite side of the world. So, depending on your budget, and I was operating CW then too, mostly. You don't necessarily have to spend a whole lot of money. You go to a ham fest, look at some of the swap shops online. I know that on QRZ.com, they have a little market there where people are selling things. And there's a few other places on the internet. Maybe a local ham might have something they want to get rid of. Um, I can tell you, I know a couple of hams right now who have a nice collection. Whether they want to give any of it up or not is up to them. But you might end up with a tube rig. You might end up with something that's totally solid state. Like I say, I have a solid state HF rig in the TS940S Kenwood that I have, and I have a hybrid in the TS520S. It has tube finals, and I have a completely solid state portable or mobile rig in the ICOM 706. And they aren't necessarily cheap, but they're not overly expensive. I can't remember how much I paid for the 706. I think it was somewhere around 1,000 for it. But the 706 was kind of interesting because it has all the HF frequencies, or most of the HF frequencies in it, as well as VHF and UHF. So it was a good little rig. Anybody have any questions, anything they want to discuss? That's all I'm going to.
Nope, I'm good.
Yeah, that's all I'm going to cover tonight. When we come back, let's see, where's. Okay, that was topic number 10. In our next session, we're going to get to, we're going to talk about the receiver. And we're also going to talk about oscillators and components. Together, those two comprise 99 slides. So we should be able to get through those rather quickly, though. So that'll be our topics on session 6, I guess, on Monday. So thanks for joining me. And I'm going to go ahead and stop the broadcast now. And again, you can drop me an email, Wayne at n3lms.net.